Thanks a lot, and thanks a lot for the invitation to participate and speak here. It's been a lot of fun the last 2 days. I didn't make it on Monday, unfortunately. So yeah, I'm going to talk about control-based variational quantum algorithms, and also after that, if there's time, I'll talk a little bit about our work in trying to design operations that are noise insensitive using pulse shaping. So that basically is the outline. So, the role of control in quantum information is pretty broad and pervasive. So we need it for initialization and readout of qubits, obviously, and we also need to use it for implementing gates and circuits, all very standard things. Now, of course, there are many ways to realize a gate. How do you decide which ones are the best? And also, quantum gates and circuits, at the end of the day, they boil down to you applying some electromagnetic waves to your device in one way or another. And so you can ask, do I even really need gates? Can I just skip all of that and cut to the chase and design pulses directly? So that'll be the motivation for the first part of the talk and also a bit in the second part. And please feel free to ask questions during the talk. I don't have to finish my slides. I really don't care. So please interrupt if something doesn't make sense. Yeah, so first I'll talk about this algorithm that's pulse-based called control VQE that we developed at Virginia Tech for quantum simulation. And in the second part, if I have time, I'll talk about a way to engineer operations using geometric ideas. Basically, ways to design pulses that do various things. So let's talk about VQEs first. So this is an idea that's been around for about a decade now, where the goal is to simulate some many-body quantum system. And we want to do this variationally, where the idea is you divide the problem between a classical processor and a quantum processor, the idea being that you're trying to use the quantum processor as little as possible. Its basic job is to store wave functions, many-body wave functions, and it allows you to measure those wave functions to get information about them. But then you want to decide how to update the wave functions on these processors by doing measurements, offloading those that measurement data onto some classical processor, processing it there, and figuring out how to update your wave function on the hardware to get closer to the target state you're trying to get to. So this is based on the variational principle of quantum mechanics that we all learn about as undergrads. So you're just trying to minimize the expectation value of the Hamiltonian with your ansatz, and we all know that for any ansatz, this expectation value is bounded from below by the ground state energy of the system. And so all the meat in this approach comes into this ansatz. How do we choose this parameterized wave function on the processor to get as close to this target state as possible? So those are VQEs. They were introduced back in 2014. And so this key question is, how do we define this ansatz? The natural way to think about it is you start with some reference state, you apply a bunch of gates to generate some more complicated many-body state. And if those gates have parameters, then you can tune the parameters to achieve many different wave functions. That's the basic idea. So then how do you choose these circuits? So there are two popular approaches that have been pursued in the literature over the last decade. One is you could call more physics or chemistry inspired, where you look at your target Hamiltonian, you look at the symmetries of that thing, and you try to write down a circuit that knows something about those symmetries. And in the case of chemistry problems, there's a famous ansatz called UCCSD, which basically encodes information about symmetries of molecules. Or you could do something which is experimentally a little bit more straightforward, which is to use a hardware-inspired ansatz, where you basically choose gates that are easy to implement on your favorite hardware. And then you build up circuits based on those gates, and then hopefully it's expressive enough that you can achieve different wave functions, and hopefully the one that you care about is in there somewhere. So those are the two most popular approaches that people have been pursuing. So here's just a quick look at experiments that have been using this chemistry or physics-inspired approach. So here I want to emphasize that these are fixed circuit ansatz. So you pick the circuit up front with some parameters in it, and then the rest of the game is to try to optimize those parameters and get closer and closer to your ground state. So these are experiments that were done in various platforms, superconducting, trapped ion, et cetera. And they get success to varying degrees. So this is the typical curve that you look at when you're studying a molecule. It's the energy versus the atomic separation between the atoms in that molecule. And you typically see a curve like this that dips down and then asymptotes to some flat value as you separate the atoms further and further apart. And you can see that in all these cases, the experimental data get pretty close to the exact answer, which is the black curves in these plots. But there are some errors. So what sort of things do you want to think about when you construct your ansatz? So there are basic trade-offs to consider. One is you want the thing to be expressive enough to be able to represent the states that you actually care about. So that's expressivity. And increasing expressivity is good and bad. So it's good because it means that, the more expressive it is, the more likely that your favorite wave function is in that set of representable wave functions for that ansatz. So the accuracy will go up. But there's this additional problem called noise or barren plateaus, where the more expressive your ansatz becomes, the harder it is to optimize, to find the correct parameter values that achieve that target wave function. And so if you have too many parameters, it becomes hopeless. You can't find that target state. So there's a right amount of expressivity that you're trying to go for. So the goal for anybody trying to do a VQE is to maximize accuracy, but to use the shallowest possible circuit to not run up against coherence time limitations. And at Virginia Tech, we've been pursuing two families of algorithms that try to achieve this balance between expressivity and optimization problems. So the first one I'll briefly mention is called adapt VQE. It's been around for about 5 years or so. It's a gate-based algorithm. And then this more recent algorithm of ours called control VQE will be the focus of this first part of the talk. It's pulse-based, not gate-based. So first I'll say a little bit about adapt to get this sense of how adaptive variational algorithms work, because both of these are adaptive. But then I want to spend more time on this pulse-based thing, going beyond the gate model and what that buys you. So here's adapt in a nutshell. So it's an adaptive algorithm, meaning that you don't pick the circuit for your ansatz up front. You let the algorithm figure that out for you on the fly, depending on the problem that you're trying to solve, depending on the Hamiltonian whose ground state you're trying to find. And what you do in the beginning of adapt is you pick some collection of operators. We call this the operator pool. And how you choose this is a really good question. We spent a lot of time on this, but I'm not going to worry about it for right now. Usually you want to pick something that's relevant to the problem you're studying. And then given this collection of operators, all adapt does is basically iteratively figure out how to keep adding exponentiated operators one by one to build up a circuit and create some ansatz that hopefully represents the target wave function after you've introduced enough operators into that ansatz. So you iteratively keep trying to add operators. You pick which one creates the biggest change in your energy expectation value at that moment in the algorithm. You add that to your ansatz. If your energy is reduced enough, then you declare you've converged and you stop. But if it's not, then you keep going. You next consider adding another operator from the pool, and you keep going. So that's basically how adapt works. And every time you add a new operator to the pool, it comes along with a variational parameter that also gets optimized at that point in the algorithm, along with all the previous parameters that you have introduced in the previous iterations. So this algorithm seems to do very, very well compared to a fixed circuit ansatz. So here you can ask, for example, how important is the order of the operators that adapt is building up this ansatz with? And so if you look at the adapt ansatz with that particular operator ordering, you get this energy versus number of parameters curve. So this x-axis you can think of as the number of iterations of your algorithm. Each iteration introduces one more variational parameter. Now, if you take that same ansatz and just shuffle the operators in some random way, or lexicographically, or for some using some other order, you find that the convergence of the algorithm becomes much, much slower. So the fact that this thing is adaptive and it's deciding which operator to insert in the ansatz at that moment in the algorithm is what gives it its power in finding the target state quickly. And if you look at UCSD, this chemistry-inspired thing, that with a fixed circuit, it's sitting there, so it's not doing very good compared to this adaptive approach. Was there a question? Yeah. Yeah, so, yeah, it's a great question. So when I want to figure out how to add an operator to my ansatz, I have to go and test it out in the ansatz and do a measurement of the gradient to see to what extent has the cost function changed. That means I'm measuring the device. And so I need to do additional measurements for each of these iterations compared to just doing a fixed circuit VQE where you have just some fixed parameters in your circuit and you just keep measuring the cost function to reduce those, to reduce the energy. Now, the fact that things converge so much more quickly when you do this adaptive approach, I'll actually come back and show later on that the overall number of measurements doesn't actually increase in most cases because the savings you have just by converging faster overcompensates for this additional measurements you have to do to figure out which operator to insert. Yeah.
So these operators A1 to AN, they are probably inspired by some insight that you have about the problem, or they are some basis for all possible operators.
So I would say it's usually the former, that usually you're picking operators with some knowledge of the problem you're trying to understand. So originally when we did this, and actually these results are for this case where we're studying a molecule, and these operators were chosen to be singles and doubles fermionic operators, which are natural for molecules. But we also showed that if you choose something completely different, like just Pauli strings that have no knowledge of this molecular structure of your Hamiltonian, they can also be beneficial depending on what you're trying to do. They can actually reduce C0 counts, although it might actually take the algorithm longer to converge.
So in some sense, this append operator with largest external gradient, that step is to avoid barren plateaus.
So the reason why we use this gradient criterion is because we want this algorithm to know the best ansatz for this particular problem that we're trying to solve. So we're not just incorporating symmetries in the form of the pool operators, we're also just asking repeatedly, okay, how should I now move in my Hilbert space to get closer to this target state? And I ask that question every time of the processor. I don't just assume it up front. Now it does show, I don't think I have a slide here for it, but we've shown that you avoid barren plateaus as a consequence of this gradient criterion, because you're essentially building up your parameter space in such a way that you're always close to a very deep global, if not local minimum in the parameter space. And so barren plateaus might show up in your parameter space if you were to explore those regions, but you just never explore those regions. Yeah.
Is the output state still chemically relevant? So, for example, did you test whether or not there's high overlap with respect to the ground state of that Hamiltonian?
Yeah, we have done that a few times. We usually just focus on the energy, but if you look at the actual wave function, it closely resembles the target state. Yeah. Any other questions? Yeah.
So when you are estimating the gradients, do you use finite difference or just use some parameter sheet like method to estimate the gradient?
So I didn't show it here, but actually if you write down the expression for the gradient, it's the expectation value of a commutator of the Hamiltonian with that pool operator. So you're just measuring more Pauli strings. And actually you can recycle a lot of the measurements you did with the cost function itself to get terms of the gradient. Okay, so that's adapt. We did a little bit of follow-up work to adapt since the original work came out. So various things we've looked at building symmetries into the pool operators. We've looked at applying it to optimization problems, not just molecules. Also condensed matter problems. In the case of condensed matter problems, we looked at a method that we call operator tiling for figuring out how to build up operator pools that know a lot about the lattice symmetry of the problem. And then more recently, we've looked at certain choices of operator pools that are especially effective in dealing with chemistry problems. And in this last work, I'll just mention briefly, we took all of these developments that we've been building up the last 5 years and we put them all into one algorithm, and we ran the thing and we compared it to the original version of ADAPT back from 2019. And so we did this for 3 different molecules: lithium hydride on the left, hydrogen 6 in the middle, and then beryllium hydride on the right. And the orange curve is the original ADAPT from 2019. The blue curve is this state-of-the-art ADAPT that was put out in this most recent paper from July, I think. And you can see that if you look at, for example, C0 counts or measurement counts, we've gotten orders of magnitude reduction in making various improvements to either the operator pool or how we do the measurements of the gradient or the cost function itself. You can dramatically simplify the circuit, etc., if you think hard about how to optimize things. And just for reference, I also included this fixed circuit example from corresponding to UCCSD, this chemistry-inspired thing, which is this diamond. And you can see in terms of C0s, we've had dramatic savings. In terms of measurement counts, there are some places where it's kind of comparable, especially if you focus on where you get into chemical accuracy. This is the shaded region here is where you basically declare victory. Your energy estimate is close enough to what you want. So this example here, for example, is kind of showing you that you're not actually really increasing the measurement counts by measuring these gradients, just because everything converges so much faster. But exactly whether you do get an overall savings or not, it depends on the problem, but it's pretty close. Okay, so this doesn't look bad. So these are like modest-sized molecules. They're kind of pushing the limits of what we could do in classical simulations of these kinds of algorithms. And you can see that you need, in the latest version of ADAPT, you need maybe 1,000 CNOS to do this most complicated problem, which is this H6 molecule. It's highly correlated. And you need on the order of 10,000 measurements. In these other cases, you don't need quite as much in terms of CNOTs and measurements. So we're kind of getting close to what we can actually do on current hardware. But I would say if you try to push this to molecules that you cannot solve classically, it's hard to say exactly how these things scale. This is a variational algorithm, so you can't make definitive statements about numbers of CNOTs or measurement counts. The only way to really know is to try. But it seems like we're still a bit far from solving things that are of practical interest. So what does this mean for us? So what I want to say next is that basically we need to move away from using gates. Gates take a lot of time. Qubits have finite coherence times, obviously, and that the time we spent generating gates is not very useful. And of course, gates are not perfect. They have infidelities, and that can also limit performance. So do we actually need circuits? At the end of the day, when I've developed my circuit, what happens after that? You take each of the gates in the circuit, you map it to some pulse, some electromagnetic waveform that gets sent into the qubits and does some operations. So what if you just skip the gate? In some sense, gates are just constraints on pulses because you're just forcing yourself to do a pulse that does this particular rotation here, and then it does this other rotation there. What if you just forget about the gate and just do a pulse that gets you from here to there directly? So this is just more of the same. Do we really need circuits when we do this? When you think about the fact that you have to compile everything down to pulses in the end. So control VQE was basically an algorithm that we developed to try to understand what happens if you throw out the gates. So here we want to do something which is again variational. It's very similar to adapt VQE, except that we're not going to update gates. We're not going to insert gates in the circuit one by one. We're going to update pulse parameters iteratively. But again, based on measurements done on the quantum processor and using a classical processor to help us figure out how to update those pulses. So it's still a VQE in that sense. And here I want to emphasize that this is a digital algorithm, not an analog algorithm, which, depending on how you define digital versus analog, you might think it's one way or the other. Here I call it digital because I'm not realizing the Hamiltonian of interest on my quantum device. I'm not tuning parameters and trying to mimic a Hamiltonian on my system. The Hamiltonian the Hamiltonian I'm trying to study only comes about by doing measurements of that Hamiltonian operator on the device. The device Hamiltonian is an entirely separate beast that has nothing to do with the target Hamiltonian I care about. So for that reason, I call it digital, because I'm not limited to any particular class of Hamiltonians. Now, but it is something which is device dependent. Now, I can no longer talk about a gate or a circuit in the abstract. Now I have to say, okay, if I want a pulse-based algorithm, what's the hardware? Because pulses are governed by the hardware that they are implemented on. And we can run this control VQE algorithm on any hardware, but just for concreteness, we're going to pick superconducting transmon qubits and see how it does in this context. So here we have some number of transmons. They all have frequencies and some anharmonicities and couplings between them. So that's the kind of system we'll focus on. The Hamiltonian of the device looks something like this, where you have frequency terms for each transmon, these anharmonicities for each transmon, couplings between transmons. And then we'll apply a driving field on each transmon separately. And so each transmon will have a driving field with some amplitude and some frequency that's applied to it. So how would you take a setup like this and make this control VQE adaptive algorithm out of it? So one way you could imagine doing it is to fix the overall pulse duration. Say it's 1 microsecond, whatever, we'll come back to that. And then given that fixed overall evolution time, start by just applying constant pulses to each of your qubits. And you can optimize the amplitude to get as close to the target state as possible, by which you can see by measuring the expectation value of the Hamiltonian. Okay, but you don't get that close to the target state. The energy is not that close to the ground state. So then you randomly pick a point in your pulse to split the pulse into two. You're effectively introducing more optimization parameters when you do that, because now I have for each of my qubits 2 pulse amplitudes. And I can allow them to be optimized separately, and then I end up with a slightly more complicated pulse for each qubit, which has some step at some point in time. And then I can keep doing this. If I'm still not satisfied with my energy estimate, I can then split the pulse again somewhere else, introduce 2 more parameters or 1 more parameter, depending on how you parameterize your pulses per qubit, re-optimize and get a slightly more complicated waveform, and you keep doing this until you get within chemical accuracy if it's a chemistry problem, or within whatever threshold you give yourself to begin with. So here we did this for a couple of simple molecules just to make sure, just to do a sanity check. So here we're looking at the hydrogen molecule on the left, and on the right, it's hydrogen, helium hydride, and then lithium hydride. And you can see that we can get pretty good results. We get within chemical accuracy after splitting the pulse 2 or 3 times in all these cases. So we actually don't need very many variational parameters to achieve the ground state. But the most interesting thing, for me at least, is that if you look at the total time to get to the solution, if I were to take an ansatz like this and translate, if I were to take this problem and look at what UCCSD gives you, translate that into some pulse for this hardware, it ends up taking 80,000 nanoseconds to get to the ground state in the case of lithium hydride. Doing control VQE, you get the same answer in 50 nanoseconds. So there's more than 3 orders of magnitude already for these really simple problems. And the reason for that is because I'm not forcing myself to do a bunch of C-naughts. The reason is because the actual target state I'm trying to get to does not have a huge amount of entanglement. That's typically the case for physics problems or chemistry problems. There's not a lot of entanglement. So if I spend all my time doing C-naughts, I'm doing maximally entangling gates, and then I have to undo the entanglement, and then I have to recreate the entanglement, and I have to undo the entanglement until eventually I get down to the right amount of not too much entanglement I'm after. And so getting rid of the C-naughts allows you to avoid this meandering through Hilbert space trying to get to your answer using these huge jumps back and forth between points in Hilbert space. So that's the reason why it's 3 orders of magnitude faster. So then you can ask, okay, how fast can I actually make this algorithm? Is there a time limit to achieve some target state? And the answer is yes. There's, for a long time, been this notion of minimal evolution time, or also known as quantum speed limits. Since the 1940s, people have been studying this in quantum mechanics. And the basic statement is that if you're trying to go from state A to state B in Hilbert space, there's a minimum time it takes to do that, given some Hamiltonian that dictates your dynamics. So for us, that shows up in this total time, this total evolution time we choose to run our algorithm for. And what you find is if you pick, for this problem here, I forget, this might be lithium hydride. If you choose that time to be 20 nanoseconds, for example, you run control VQE, you get some complicated pulse shapes. And now you reduce the time a bit to 16 nanoseconds, you rerun control VQE, and it gives you slightly less complicated pulse shapes. And then what you find is that as you keep reducing this evolution time, eventually you just end up with a pulse shape where on each qubit you're applying a pulse that basically has a bang-bang structure, meaning that you're always saturating the pulse amplitude bound, whatever that is, at every time during the evolution. So the time optimal waveforms are always square waveforms where you're just saturating the lower bound on the amplitude, and then you jump to the upper bound, lower bound, upper bound. How many times you jump and at what times you jump, those are things you cannot predict a priori. But the fact that you saturate the amplitude bound is just based on a well-known theorem called Pointryaghin's maximum principle, which says you're always saturating the bounds on your pulses if you're achieving the time optimal evolution. So here what we're seeing is that as you get close to 15 nanoseconds, a little bit less than that, this is the minimum time it takes to prepare this ground state for this molecule on this hardware. And you cannot do better than that. Now, another interesting thing about some types of hardware, like transmons, is that they they're not just two-level systems. They also have higher levels, infinitely many higher levels. And especially if you're looking at transmons where the n-harmonicity, the spacings between the levels are pretty close as you go up, it's almost a harmonic oscillator. The existence of those higher levels can matter a lot for how the system evolves. Those higher levels can easily get populated, and you have leakage. And leakage is usually considered a bad thing. You know, it means you're leaving the computational space, you're generating errors, you don't get quite the state that you want. But in the context of this pulse-based algorithm, it's actually not necessarily a bad thing. And what's interesting is that we find that if you model this system and just keep the lowest two levels of each transmon, that's the blue curve here. And you can see that as you reduce the total evolution time from 20 nanoseconds down to 17, 15, eventually you find you can never get to the target state. That's telling you this drop-off tells you you've hit the minimal evolution time for that problem. If you include the third transmon level in your simulations, now the minimal evolution time drops down to less than 10 nanoseconds. So you can actually speed up the time to solution by including the higher levels. And a simple way to understand why that is because you're basically expanding the solution space. You know, at the end of the day, you care about what does the wave function look like in your computational space. And if you strictly say, I don't want any leakage at all, there's no footprint of my wave function outside the computational space, and there's a unique solution that you're trying to find, and there's a unique time it takes to get there. But if you say I don't care what the wave function does outside the computational space, so long as the footprint in the computational space is what it's supposed to be, namely the ground state of this molecule, then anytime I change the wave function in such a way that the stuff outside the computational space changes, but not the footprint in the computational space, then that's a different solution to my problem. So now I have a continuous space of solutions, and some of those solutions will actually be closer to my initial state than the solution where I have strictly no leakage. And so I can get a speed up as a consequence. And so long as I have enough of a footprint in the computational space, I actually don't care if there's leakage, because I can still extract the energy, I can still measure other observables on that state that's been prepared, that are living in the computational space. The fact that there's leakage doesn't really matter. If there's too much leakage, then I don't have enough data about the computational space, in which case I can't get information at all. So I don't want to have 100% leakage, but large amounts of leakage don't actually matter. Yeah, and then very recently we've put out another work where we were interested in understanding how, as you change the parameterization of the pulses you apply on the hardware, how does that impact the performance of the algorithm? And in this work we looked at a couple of things. So one question we had was, how does the number of windows in your pulse affect how quickly you get to the solution? So if I have many windows, meaning many pulse parameters per qubit versus few pulse parameters per qubit, is there a dramatic effect on how the energy error looks as a function of the pulse duration? And the short answer is that no, it doesn't actually matter too much. And in fact, if you have too many time windows, it actually makes things a bit worse, not better. So you don't actually need that many variational parameters for the examples that we've looked at. And moreover, if you look at the optimization process, so here the y-axis is basically a measure of how complicated is the optimization process for those pulse parameters. You can see that if you have too many pulse parameters, it just gets really complicated to optimize. But sticking with a few parameters, you're pretty safe throughout. And then on this side of the slide here, we were looking at different ways to parameterize parameterize the pulses. For example, you could talk about Cartesian parameterizations where you have an x component and a y component of each complex pulse. Or you could do a polar type parameterization where there's an overall amplitude and then a phase. And interestingly, we're finding that the Cartesian parameterization seems to do quite a bit better than the polar one, but we don't have a clear understanding of why that is yet. Was there a question? Yeah. So are we adjusting the learning rate? Yeah, this is just a gradient descent type algorithm. Yeah, so yeah, more windows means more pulse parameters. I'm not quite sure what you mean. Do you mean like, in the gradient descent, do I choose sort of the size of each step according to the number of parameters? Yeah, I don't think we made that part adaptive, but I'd have to double check. But the fact that it's quite a bit more complicated for more parameters is more or less what you would expect. I don't know. We should talk afterwards whether, if you adapt it, maybe it's not as bad. Yeah, yeah. I see. Yeah. Yeah, that's a great question. Yeah, so in this simplest example, yeah, so the question was, what about the fact that I'm looking at pulses that have these abrupt changes in them, and what happens as I try to smoothen the pulses? So actually, I was looking at square waveforms just for simplicity, because it's the easiest thing you can write down. You could easily pick a different basis for your pulses. You could do, something which is nice and smooth, Slepians, which are nice bandwidth limited pulses. You could choose anything you want, really. And in some of these works, we've looked at other things like sinusoidal type parameterizations of pulses and other things, but it doesn't really impact anything at all.
When you smoothen it out, does it change the accuracy?
So, yeah, so I would not do this by, finding some solution in terms of square waveforms and then smoothing that out and then putting it on the hardware. The way this would actually be run is you start with pulses that already respect whatever bandwidth constraints you have on the hardware. You optimize those directly, and that will give you some solution. And we have not seen any evidence that the optimizer cares much about bandwidth constraints. It does seem to care about how you parameterize the pulses in general, but bandwidth constraints in particular are not necessarily problematic. Now, I would expect that as you impose stronger and stronger bandwidth constraints, that's going to increase the minimal evolution time, the time it takes to get to your solution, but that's just a fact of life. If you cannot achieve those waveforms, then that's just going to change what your device can do, obviously. Yeah, question? So I think in all the results I've shown you, these are fermionic Hamiltonians describing small molecules. Ones you can map onto 2 or 4 qubits. Yeah, so these are like hydrogen, lithium hydride, things like that.
Can you comment on, right, with larger fermionic systems, you would expect these types of Z strings to interact. So then how would you kind of enforce that constraint on the pulses to have these longer interactions?
Oh, so actually, I don't really care about Z strings in terms of the ansatz itself. So even in the case of adapt VQE, the gate-based version of the algorithm, so I didn't talk about it, but if you make an operator pool that is designed for a chemistry problem, nominally you would, if you're just translating singles and doubles fermionic operators into Pauli strings, you have these long Z's under a Jordan-Wigner mapping. But we found that if you just throw out the Z strings and just keep like the weight between the X's and the Y's that you actually care about, there's no change in the performance of the algorithm. So in that case, the only place where the Z strings show up is when you actually measure the Hamiltonian terms. So the ansatz itself doesn't actually care about the Z strings. Oh, but you don't, there's no reason to impose a constraint on the form of the steps you take to get to the target state, right? The final target state, if you were to map it back into fermionic operators, should have the Z structure built into it. But the way to get there's no reason to impose that you restrict yourself to these particular steps in Hilbert space to get to the target state. So you have a lot of freedom in choosing these operator pools. You can choose ones that are fermionic in nature and have the Z strings. You can start with the fermionic ones, throw out the Z strings. The performance doesn't change. We actually have shown that in one of the early papers. You can forget about fermionic operators entirely and just focus on Pauli strings of various sorts. It still works. You're just choosing different paths in Hilbert space. So any other questions? Yeah.
Sorry, I'm not helping us. So, like, if you have more leakage, like,
So none of the results I've shown have errors included in them. So the expectation is that for variational quantum algorithms, If you have coherent errors in the gates, you don't expect that to matter much because you can compensate those by just changing the optimization of the parameters later on in later steps. So the variational principle kind of takes care of that. I think what are more concerning are errors in things like readout, where you're doing a bunch of measurements at intermediate steps and you're using those measurement data to inform what you do next. And if those data are inaccurate, then you have an issue going down the line possibly.
Right. Sorry, I guess the question is more about like there's this very nice kind of intuition that like you can bring the total time and so like there's a certain limit of that. Like after you including the effect of loss, like will that kind of intuition be affected and like in terms of how like maybe how long the pulse it takes to converge and like what is the accuracy of the
Yeah, I think it's a good question. If you take loss into consideration in this control VQE algorithm, does that actually impact the minimal evolution time? Yeah, that's a question that nobody has explored so far. It is true that in the context of quantum speed limits more broadly, there exist results for open quantum systems, and you can write down expressions that the optimal time should obey in that context, and they are different from the ones you have in the absence of the leakage channels, et cetera. But we haven't looked at that in this algorithm context. Okay, so I still have how much time? 10 minutes? Okay. Yeah, so then in the last few minutes, I'll just say a little bit about this geometrical engineering of control fields. So here I mentioned both error suppression and fast operations. So essentially, what I want to do is to also think about this going beyond Gates' idea, to think about how we can find a broader class of solutions if we want to do something like dynamical noise suppression, so that we have this idea of dynamical decoupling where you send in a bunch of pulses equally spaced in order to suppress dephasing noise along some axis or something like that. These are techniques from NMR that were developed back, starting in 1950, and they've been widely used in quantum computing applications and in quantum information science in general. And so I guess the question I want to try to address in this part of the talk is how can I move away from these sorts of very rigid forms of dynamical decoupling or dynamically corrected gates and look at a much broader class of ways to achieve the same thing. So let me be more concrete. So here's Hahn spin echo. So this was first proposed back in 1950 by Hahn, where he said, okay, we can deal with dephasing issues in nuclear magnetic resonance type experiments if we apply 1 pi pulse about, say, the x-axis halfway through the evolution. And if you have a fluctuating magnetic field in the z direction that's slow, the fluctuations are slow, then applying this pi pulse halfway through will refocus your spins so that it's essentially as if this noise did not exist at the final time. So that's the simplest version of dynamical decoupling. It's been generalized to multi-pulse sequences like CPMG, it's probably the most famous one. And it's been applied to all kinds of hardware in the space of quantum computing. Spin qubits in semiconductors, superconducting qubits, trapped ion systems, etc. So it's been very effective in preserving quantum states. But of course, in practice, we don't want to just preserve some quantum state. We also want to be able to do operations on it. And we need to be able to do operations while suppressing the noise at the same time. So of course, by operation or gate, I just mean the evolution operator at some final time. And so suppose, let's take the simplest case of some single qubit Hamiltonian like this. And I have some driving field omega of t that has some amplitude omega of t here. And then there's some detuning parameter delta. And both of these things could be fluctuating as a consequence of interactions with the environment of the qubit or errors, issues in my AWG that generates the waveform in the first place, et cetera. And the goal in dynamical decoupling or dynamically corrected gates is to achieve some target operation to leading order in such a way that you're somehow suppressing these error terms. And what you want to do is choose your pulse omega of t in such a way that you're canceling at least the first order in epsilon and the first order in delta omega. So that's a simple example of dynamical decoupling in this more general setting. So this problem is challenging depending on the type of hardware you're looking at. In some hardware, you have lots of constraints on what the control fields can do. For example, we looked at a spin qubit system in gallium arsenide a long time ago. That was my introduction to this problem. And we were tasked with trying to come up with some universal single qubit gate set that could suppress two types of noise, the two types I just showed you on the previous slide, with the constraint that your control field always has to be positive, because this is a singlet triplet qubit, and that has this constraint. And if you look at and we found a solution to this problem where we're just using like square pulses, so there's some square pulse sequence that can deal with both types of noise at the same time. You can think about this as you're basically doing some sequence of gates, right? Each time segment here is implementing some evolution. There's some gate operation that's happening. And so this is really, I'm just splicing together a bunch of discrete gates in such a way that the end result is that they're canceling the noise and achieving the target operation. And the reason why we looked at square pulses is because mathematically it's easy to solve the Schrodinger equation in this case. And that's exactly why people in NMR have focused on square pulses and delta functions for the last 70 years, because everything's analytical. So when I went to an experimental collaborator to try to implement this in the lab, we ran into the problem that they can't actually create a square waveform in the laboratory. There are bandwidth constraints. You cannot make the rise time infinitely fast. And at the end of the day, this thing did not quite work. It was close, but not quite there. And the request I got from my collaborators was to come up with something similar, but based on smooth waveforms that they can actually implement with high fidelity in the laboratory. So I went back to the drawing board, and I tried to think how you can do the same thing with an arbitrary shaped pulse. And so let's again look at this single qubit. So I'll just take a minute to explain the basic idea and basically stop. So I have a driving field along the x-axis, some noise along the z-axis, which is, so epsilon is a random but constant variable. It's constant during the pulse, but it can change from one pulse to the next. And my goal is to choose omega of t such that this epsilon is canceled, at least to first order. So to figure that out, I can do a perturbation series expansion of the evolution operator, order by order in epsilon, and then I can try to make these coefficients of epsilon, or powers of epsilon, vanish at the final time. And so in this particular problem, these coefficients have this nice recursion relation among them. And if you were trying to derive Hahn spin echo, CPMG, any of that stuff, you're basically looking at these conditions and figuring out when should I apply my pi pulses such that this integral vanishes at the final time. But now I want to do this with a smooth pulse. And to get a handle on this, what we did is we just took the first leading order coefficient here, the one multiplying epsilon, and we just plotted it in the complex plane. It's a complex function. It's part of the solution to the Schrodinger equation. And it starts at the origin in this space, and as time progresses, it traces out some path. So this is just a definition of this coefficient. And you can call this the error curve because it's basically giving you a measure of how much the error is impacting the evolution. So that's kind of trivial, but what's interesting is that if you stop at some time and look at the bend of the curve at that point, the curvature, it's exactly given by the pulse. And that statement is not so trivial, because what I'm trying to do is I'm trying to cancel the noise, which means I need this curve to come back to the origin at the final time, so that at least the first order noise term is canceled. And my goal is to find a pulse that does that. Well, if when I draw this curve, the pulse is just the curvature, I could just draw a closed curve and read off the pulse from the curvature. So this is the general solution to this dynamical decoupling problem. Any closed curve I draw will give me a pulse that cancels noise while implementing my favorite gate. In this particular example, it turns out that the gates you're implementing are x rotations by construction. And the particular x rotation you get is determined by the opening angle of the curve you draw, the opening angle at the origin. And so any closed curve with a given opening angle will give you that same x rotation while canceling noise to leading order. And if you look at the famous 19th century mathematicians, they all had their favorite Lemnis gate, which just means figure 8. So if you want curves that have nice analytical formulas, you could just take these and chop them in half to get your closed curve. So Gerono had one, Bernoulli had one. These are the examples from those guys. And you can read off the pulse by computing the curvature. There's some simple formula. It's basically the second derivative of the curve. Yeah, so this is a general solution to the problem. I've not assumed anything. So I should be able to go back to Hans Spinecco, CPMG, et cetera, and understand those solutions in this geometric language. So here is Spinecco. Here I start at the origin of this parameter space. Initially, there's no pulse. No pulse means no curvature. No curvature means a straight line. So in Spinecco, initially I go up a straight line, and then halfway through the evolution, I turn around infinitely fast because I have an infinite pulse. That means infinite curvature, so I turn around infinitely fast by 180 degrees. And then I come back along the same straight line, and I stop at the origin at the end. And so at this point, noise is canceled. And any other delta function pulse sequence, for example, CPMG, corresponds to just going up and down a line multiple times. Every time you turn around, you pick up a pi pulse. And so in CPMG, you have this line segment here. Now you're starting in the middle. You go up, you turn around, you come down, you overshoot the origin, and you turn around down here, which means that the pulse spacing here is twice what it is in the beginning, which is the characteristic of CPMG. But you can keep going up and down as much as you want. Every time you turn around, you pick up a pi pulse. So that's CPMG geometrically. But the general solution for this problem is to get off the line and draw curves in 2 dimensions. And any closed curve I draw gives me a solution to this problem. So there's a huge space of solutions. And as soon as I draw the curve, I already know more or less what the pulse looks like because it's given by the second derivative of the curve. And I also know how long it takes because I didn't say this earlier, but the total evolution time is just the arc length of the curve I draw. So I know immediately how long the pulse takes and what its shape looks like. And I know that it cancels noise and it implements my target operation. So all that just by drawing. I don't have to do anything else. You can ask, okay, what happens if I want to cancel higher order noise? It turns out that there are certain constraints. Well, actually, it's simple. You just have to make your curve have vanishing enclosed area. That'll take care of the second order noise term. So these are 4 examples of closed curves with vanishing area. So they're second order robust. And these ones that are nice and symmetric implement identity gates because the opening angle at the origin is always the same. It's given by pi. But if you look at less symmetric ones that have different opening angles at the origin, you get different X gates that are all second order robust. So we've taken this in a number of directions. We keep finding interesting discoveries that, if you want to combat this other type of noise, oh, well, the space curve has to satisfy this other property, which is a nice simple geometric interpretation, and so on. If you want to find the fastest possible pulses that cancel noise, you can just notice that the length of the curve is the pulse time. So you're trying to minimize the curve length. And of course, you could just take some closed curve and shrink it arbitrarily, get faster and faster pulses. But as you shrink the curve, you're making the curvature arbitrarily large, which means you're violating at some point your pulse amplitude constraint. You're going beyond what you can actually do in the physical hardware. So you should impose a constraint on the curvature to avoid that. And then you can try to solve this variational calculus problem where you're trying to minimize the curve length given some bound on the curvature. So this is what the action looks like. The equations of motion for this thing are trivial, it turns out. The solutions are straight lines and circular arcs. The absolute minimal length curve is this thing made up of 3 circular arcs. You cannot do faster than that. Circular arcs translate to square pulses. So this is a 3-part composite square pulse. This is the time optimal solution for this X-gate problem with dephasing noise. Of course, I started by saying I don't like square pulses, but then you can impose those bandwidth constraints as additional constraints on the shape of your curve and get away from these infinite rise times. Yeah, so we've generalized this to more types of noise, different types of noise. You can go to higher dimensions. It all more or less works the same way. We keep getting surprised by how simple the constraints you want to impose become on the geometric side of things. I won't go into the details. You can do this for any finite dimensional Hilbert space. I don't yet know how to do it for something like a bosonic mode that has infinitely many levels. But for any finite dimensional Hilbert space, you can draw a space curve that represents the evolution of that system. And if you want the noise to cancel, you can impose constraints like closing of the curve, the certain areas have to vanish, etc., to make that happen. And you can always read off the control Hamiltonian by computing derivatives of the space curve. So we've done it for 2-qubit systems, et cetera. And here are a bunch of papers. If you're interested in learning more, this is a good place to start. There's this review article I rewrote a couple of years ago. Yeah, so then let me just stop by acknowledging my collaborators. So Sophia, Nick, Ayush, and Kyle, I work closely with on the control VQE stuff and also the original adapt. And then on the space curve side of things, my students Hunter and Vagelis have done a lot of really nice work. And then let me just advertise our relatively new center in Virginia Tech. We are about 15 or so faculty right now, almost all theorists. One experimentalist, but we're hoping to rectify that. Yeah, and we always have postdoc positions, and we're always looking for students. So yeah, I'll stop here. Thanks.
We have time for 2 or 3 questions.
Thank you for the great talk. For the results that you were presenting, I think for the first half or so, it looked to me like it was all running on simulators of exact systems. Was that correct?
Yeah, that's correct.
Okay. Have you tried on real hardware, any of these tools?
That's a work in progress. So actually, we're working with AQT. We heard it from Ravi previously to try to run this on their hardware.
Cool. What do you think of Q control? They've proposed to do very similar things, but more with like machine learning rather than analytics.
Yeah, I think so I see that as very complementary in the sense that the space curve approach allows you to get kind of a bird's eye view on what the solution space for these pulses is. You can identify what is the time optimal solution. You can relax your control constraints until you get a really simple model and understand, okay, this is the absolute best I could do in the simplified version of the problem. And then you can expand from there, add in more constraints based on the system that you have. And I think that's where things like Q controls work with machine learning or just generally optimal control theory, numerical recipes can get you more finer results starting from that initial point. And we've used that quite a bit in the way we've done things.
Thanks for the nice talk. So the last part is really interesting. So I'm curious, you mentioned continuous variable. So if I look at the state evolution in the phase space, instead of a trajectory, a points moving, it's going to be a distribution. It's
Yes.
like, and then all I have to do is trying to think, okay, integrate over the distribution of the Wigner function, and it seems doable in some sense, but I think we have to find a noise channel representation in the phase space. That's something that still maybe some work, but it feels doable in some sense.
Yeah, I've thought about it a little bit. You can write down Wigner functions for spin boson systems, conjoined Wigner functions, and so on. But yeah, I think part of the issue is what you said, that understanding how to think about the noise is a little bit unclear. What sort of constraints would you be imposing? What's the analog of the closed curve constraint in that context? I haven't quite figured that out yet.
Okay. And second question on that is the Hamiltonian you write down with arrow is sort of still unitary evolution. What if I have some non-unitary some noise? Does the noise robust sort of control here still works, or is there a generalization for that kind of?
Yeah, so the short answer is I don't know. There's something that we're looking into now, but I don't have a clear answer to that yet.
Okay. Yeah. Thank you.
Are there any more questions? If no, let's thank the speaker again.